Welcome to The Explainer. We're here to break down big topics into clear, understandable pieces. All right, let's jump right in. Think about this for a second. What's the invisible chemical thread connecting, say, an LPG cylinder, a plastic bottle, and even your perfume? I mean, they seem totally different, right? But believe it or not, they all share the same basic chemical blueprint. What do you think it is?
The answer is hydrocarbons. Yep, these are the quiet, unseen architects of pretty much our entire modern world. They form the backbone of so many materials and fuels that we rely on every single day, often without even thinking about it.
So, what are they exactly? Well, the name is actually a huge clue. You've got hydro for hydrogen and carbon for, you guessed it, carbon. That's it. They're organic compounds made up of only those two elements. They are the main thing you'll find in petroleum and natural gas, which basically makes them the foundation of our entire energy and materials economy.
But here's the thing. Not all hydrocarbons are the same. It's a really diverse family, and each member has its own kind of personality. So let's start with the simplest, most stable members of the group, the alkanes. You can think of these guys as the solid, dependable bedrock of the hydrocarbon world.
What makes an alkane an alkane? It's actually super simple, but really powerful. Every single carbon atom is connected to another one with just a single bond. That's it. This strong, stable bond, called a sigma bond, is what defines their entire character. Okay, so this single bond structure gives them some really specific properties. First, because they only have single bonds, they're holding on to the maximum number of hydrogen atoms possible. That's why we call them saturated. They're full. This also makes them really stable, so they don't react with much. In fact, they used to be called paraffins, which literally means little affinity. But here's the twist. That stability is exactly what makes them incredible fuels. They're just fantastic at storing energy and then releasing it when they burn.
And you see this in action all the time. The quote on the screen says it all. LPG cylinders contain propane and butane. Propane, butane, those are classic alkanes. So yeah, every single time you turn on your gas stove, what you're really doing is tapping into the stable, energy-packed single bonds of these simple little molecules. All right, so if single bonds mean stability, what happens when you shake things up a bit? What if you introduce multiple bonds? Well, that's when we get into the world of alkenes and alkynes. These are the more reactive, unsaturated members of the family. So, what's an alkene? Its defining feature is at least one carbon-carbon double bond. Now, this double bond has a weaker part, a pi bond, where the electrons are held a bit more loosely. This loose hold creates a spot with a lot of electron density, and that makes the whole molecule way more reactive than a stable old alkane. So, what's all this reactivity good for? Why would you want it? Well, check this out. The slide notes that ethylene polymerization is used to make plastic. Ethylene is the simplest alkene you can get. It uses that reactive double bond to link up with other ethylene molecules over and over again in a huge chain reaction. And that super long chain, that's polyethylene. You know, the most common plastic on the entire planet. So here we can see the two unsaturated cousins side by side. Alkenes, with their double bonds, are reactive enough to make plastics. But alkynes, they take it to a whole other level. They have a triple bond. That's one strong sigma bond and two weaker pi bonds. This makes them even more electron-rich, even more unstable, and it packs a crazy amount of potential energy into that tiny molecule. And where do you see all that high energy in the real world? How about welding? The quote says, acetylene is used in welding. Acetylene is just the common name for ethine, the simplest alkyne. When you burn it with oxygen, that high-energy triple bond just unleashes a massive amount of heat. We're talking a flame hot enough to literally melt and fuse solid steel together. That's serious energy. Okay, now for our final group. And this one is a really special, kind of unique class of hydrocarbons. We're talking about the aromatics, and they're all about one famous structure, the benzene ring. And right away, benzene presents us with this fascinating little puzzle. If you look at its structure, it looks super unsaturated. It's got 3 double bonds. So logically, it should be really reactive, right? Just like an alkene. But it's not. It's surprisingly stable. It doesn't want to react like alkenes do. And that leads to the big question. Why? Yeah, how is that even possible? How can a molecule have all those double bonds but act so stable? What is benzene's secret? The answer is a really cool concept called resonance. See, those double bonds aren't actually fixed in one spot. Instead, their electrons, all 6 of them, are what we call delocalized. They're basically being shared equally among all 6 carbon atoms at the same time, creating this amazing continuous ring of electron density. And that sharing, that delocalization, is what makes the whole molecule incredibly stable. It's also why they're called aromatics. A lot of these compounds have very distinct smells, or aromas.
And you encounter this aromatic property all over the place. Just like the quote says, benzene derivatives are found in perfume, paint thinner, and petrol. It's that unique, stable ring structure that gives all those things their characteristic and often very powerful smells. So there you have it. We've seen how these different hydrocarbon families literally build our world, from stable fuels to reactive plastics. But, and this is a big but, their widespread use, especially burning them, comes with some really significant consequences. So let's take a look at the hydrocarbon footprint. One of the biggest problems is something called incomplete combustion. This happens when hydrocarbons burn, but there isn't enough oxygen around. Instead of just making harmless carbon dioxide and water, they can produce soot, that black stuff, and much, much more dangerously, these complex things called polynuclear aromatic hydrocarbons. And a lot of those are known to be carcinogenic. That means they can cause cancer. And this isn't some abstract chemistry problem. It has severe, real-world impacts on people's lives. This quote really brings it home. Hydrocarbons are a major contributor to Delhi's smog. All those unburnt hydrocarbons pouring out of cars and factories, they are a primary ingredient in that toxic air pollution we see in so many cities. It's a massive public health crisis. Okay, so let's do a quick recap. It really all comes down to the type of bond between the carbon atoms. That one thing determines everything. You got the stable single bonds of alkanes, perfect for fuel. The reactive double bonds of alkenes, great for making plastics. The super high-energy triple bonds of alkynes, ideal for things like welding. And then you have that special stable ring of the aromatics, which gives them their own unique properties. So, from our energy to our everyday materials, you just can't deny it, hydrocarbons are the foundation of modern civilization. But, as we've also seen, our dependence on them creates these huge challenges for our health and for the planet. And that leads us to the final, really crucial question that we all have to think about. So, if this explainer was helpful for you, please do like, share, and subscribe to the apathsolid.com channel. That way you won't miss out on more videos to help you with your NEET and JEE preparation.